Hello friends, I am Lalit Vasist. I welcome you all on my YouTube channel Engineering Made Easy. In the last lectures, I discussed Pulse Amplitude Modulation PAM. In this lecture, you will get the concept of Pulse Width Modulation PWM. It is also known as Pulse Duration Modulation PDM. Actually, the pulse width modulation is a type of pulse time modulation PTM. Pulse time modulation is of two types. So let me tell you. Pulse time modulation. This pulse time modulation is of two types. These two types are pulse width modulation PWM. It is also known as Pulse Duration Modulation. Pulse Duration Modulation PDM. The another type of PTM is Pulse Position Modulation PPM. Pulse Position Modulation PPM. Okay, so before knowing pulse width modulation, let me first explain you what is pulse time modulation. So here I am going to tell you what is pulse time modulation. Pulse time modulation. Okay, in short it is known as PTM. So what is this PTM? In PTM, the timing of the pulses of the pulsed carrier is varied. So the variations occur on the time axis. Therefore, this kind of modulation is known as pulse time modulation PTM. So let me write the definition here. In PTM, the timing of the pulses of the pulsed carrier is varied. So the variations occur on the time axis. Okay, therefore this kind of modulation is known as pulse time modulation. Therefore it is known as pulse time modulation. Okay, since in pulse width modulation also the variations are present on the width, or we can say the duration that is on the time axis. So it is a type of pulse time modulation. Therefore, this pulse duration modulation or pulse width modulation is nothing but a type of a pulse time modulation. Now we will understand what is pulse width modulation. So for this, first of all, let's start it with the definition of pulse width modulation. So first let me define it. What is pulse width modulation? So what is this? In PWM, the width of the pulsed carrier wave is varied as per the instantaneous value of the message signal. It is also known as pulse duration modulation, as I have told you earlier. So in PWM, let's write it. In PWM, the width of the pulsed carrier wave, the width of the pulsed carrier wave is varied as per the instantaneous value of the message signal. As per the instantaneous value of the message signal. This message signal is also known as modulating signal. So this modulating signal and message signal are the same thing. So it is known as the pulse duration modulation, PDM. Now I'm going to draw a few waveforms to make the concept of pulse width modulation more clear. So let's draw a few waveforms. You will get the concept easily with the help of these waveforms. So first of all, let's draw the modulating signal or the message signal. Let me draw first the axes. Here in all the cases, here it is the time axis represented by T, and here I will draw the modulating signal. Okay, and here the carrier wave. Okay, and here I will draw the PWM wave. So let's start. This is a sinusoidal kind of sinusoidal modulating signal. So Now it's time to see the carrier wave. This carrier wave has equal amplitude of each pulse. It is simply a train of pulses having constant amplitude and constant width of the pulses, and these have equal space between the pulses. So it is a train of pulses. So what is this? It is a train of pulses of equal amplitude and widths. Okay, so it is nothing but the pulsed carrier. Okay, it is the pulsed carrier wave. So now let's see the diagram of PWM wave. So here I am drawing these dotted lines. Corresponding to these some important points, like the minimum point of this modulating signal, the maximum, and points where it crosses the x-axis. So we can draw the graph easily we can analyze it properly with the help of these dotted lines. So let's draw this. As I told you in the definition of PWM, that the width of the pulses in PWM, or we can say the width of the pulses of this pulsed carrier wave, varies as per the changes in the amplitude of this modulating signal. So how does this happen? Actually, the width becomes maximum at where the maximum of this modulating where the amplitude of this modulating signal is maximum, and minimum where it is minimum, and some intermediate widths at other points. So the width will be some at this point, and it will increase, will become maximum at this point. It will start decreasing and decreasing, and at this point the width of the PWM will become minimum, and it will again start rising. So let's see how does this happen. Let's draw some width corresponding to these 3 points where it is crossing the x-axis. So these all are of equal widths. Okay, amplitude is same for PWM, and now the width corresponding to this peak value is maximum. As it is maximum, it is varying as per the amplitude of the message signal or the modulating signal. Since it is maximum, so the width is maximum at this point. So let's draw. Okay, this width is maximum, and at this point it is minimum. Okay, so this is the minimum, here it is maximum, so here also it is maximum width, and here it is minimum width. Okay, and at these 3 points, this and this, have equal widths. We have equal widths at these 3 points. So this is what? This is CT, carrier, pulse carrier, and here it is the PWM, also known as PDM, Pulse Duration Modulation. This PWM waveform, you can see here that it has equal amplitudes. All have equal amplitude, all these pulses have equal amplitude, but the information lies in the width of the pulses, and the width is varying as per the variations in the amplitude of the modulating signal. So the information is contained in the widths, not in amplitude or relative positioning of the pulses. Okay, here from the waveform diagram you can easily analyze that the amplitude of the PWM waveform is constant, but the width or duration of the pulses is varying. This variation in widths is according to the change in the amplitude of the modulating signal. As you can see here, the amplitude of the PWM pulses is the same. Because of this, not only it is less affected by noise, but also the separation of the noise is easier as compared to the pulse amplitude modulation, because in pulse amplitude modulation the amplitude varies. So one very good thing about PWM is this, that it is, because of its constant amplitude, less affected by noise. So let's write it. PWM is less affected by noise due to its constant amplitude. Okay, it is also easier to remove or separate noise from the signal as compared to PAM. Okay, so one more thing that you should notice here, this thing is related to noise, and now I am going to tell something about power. So what is this? One more thing that you should notice here about PWM is that in PWM, because of changing widths of the pulses, the instantaneous power of the transmitter varies. This power variation was due to change in amplitude in case of pulse amplitude modulation. Okay, but here it is because of the change in widths. In pulse width modulation, it is necessary that the transmitter must be able to handle the power content of the pulse that has maximum pulse width. Okay, so let me write it, that in PWM the instantaneous power of the transmitter varies. Instantaneous power of the transmitter varies, and this power variation is due to change in amplitude. Okay, sorry, this power variation is because of the change in width of the pulses due to variations in the widths of the pulses. Okay, so in PWM the power varies, and I also told you that it is necessary that the transmitter must be able to handle the power content of the pulse that has maximum pulse width. So keep it in mind. In pulse width modulation, the pulse width modulation is very similar to frequency modulation. This is very interesting thing, that the pulse width modulation is quite similar to the frequency modulation. The PWM is very similar to frequency modulation, FM. How? Because as we know that in FM the frequency of the carrier wave varies as per the modulating signal, and the frequency is nothing but simply the inverse of the time period. So because since in FM frequency of the carrier varies as per the modulating signal, and frequency is nothing but the inverse of time period. So we can say that the time period varies. So in the same way, in PWM the width, which is nothing but the time duration of the pulse, varies according to the modulating signal. Similarly, in PWM the duration, which is nothing but the time period or the time duration, varies. Okay, so it is the same thing. It is quite analogous to the frequency modulation. Okay, so friends, did you get the concept of pulse width modulation? If you have any question regarding this lecture, please don't hesitate to write in the comments. If you liked my video, then please subscribe my channel, Engineering Made Easy. By subscribing, you will get notification of my new uploaded videos. Thank you for watching. See you tomorrow in the next video. Bye bye.